My name is Corstian Boerman, and welcome to this session on titled How Complex Software Impacts Your Cognitive Abilities. Before we start, I'm curious about the sizes of the teams we are working in. So let's do a raise of hands. One of you is working on their own. I see 3 people. Who's working in a team of 2? Also a few. 3 or 4? Almost a quarter of the room. Between 5 and 10. It's like half the room. And then I suppose the remainder of you work in teams larger than 10 persons. Seems like I'm missing some people. I'm a freelance software developer from the Netherlands, and for all of my career I've been working in small companies. When I was 17, I started my software development career in a small company, straight out of high school, and I worked there for about 4 or 5 years until I burned out. And this, at the time, was the end of my story. But for this talk, it will be the beginning. So in these 4 years, there was a mismatch between my abilities and the expectations of my abilities, which led to my burnout. And so I was expected to deliver more software at a higher pace with better quality. And so this imposed expectation, in a certain way, was amazing for my learning experience, though absolutely devastating for my well-being, as evident by my burnout. There is one interesting aspect about burning out, and that is that people who are burning out have the tendency to make themselves obsolete before they, in fact, burn out. So the impact on the business of these people is pretty much limited. And instead, these individuals bear the whole weight of this experience themselves. And so, while I was burning out, there was a race to the bottom between my cognitive ability and the rate at which I could simplify the software I was working on. Until up to a certain point, I wasn't able to simplify my software even further, and my cognitive abilities declined even faster, and that was the point where I definitely burned out. And so burnout is associated with a decline on 3 main cognitive functions, which are your executive functions, your attention, and your memory. So at that point, as a software developer, I was basically worthless. And at that point as well, I had been writing code with mental capacity comparable with that of a 4-year-old. I'm kind of surprised how I made it work. But this experience guided me thereafter to write simpler code, which took less effort to understand. And to a certain extent, it is still a necessity for me, since I never really recovered from this burnout. So in order to be able to work as a software developer, I must absolutely work with code that fits in my head. And I can only, where a normal person supposedly can remember about 5, 6, or 7 aspects at the same time, I have to do with 2 or 3. So that's a severe limitation on my side. And so to deal with cognitive demands, we can basically do 3 things. We can allow the implications to happen, and this results in degraded quality of the products we're building. But perhaps worse, this results in decreased developer well-being. Alternatively, we can temper the business demands. So we can go to our customers and tell them to tone it down a little bit. Or alternatively, we can split up the complexity. We can distribute the work over a bigger team. Or we can create boundaries to deal with the complexity that we face. And that is where I will put the focus on in this presentation. But first, let's visit the notion of cognition. Cognition is something which is often discussed on a conference like this in the context of cognitive load or cognitive complexity. But what is cognition really? And I want to share the definition of cognition with you, which is the mental action or process of acquiring knowledge and understanding through thought, experience, and the senses. So, in our software, this relates to the software development process as follows, where we integrate these three aspects in our knowledge and understanding, where knowledge can be seen as contextual information we need to remember, and understanding are things we can deduce. But this is a process which takes time, and that's probably what makes software development so expensive. Recently, we have seen a shortcut being made in this process, and it looks like this, where we use large language models to develop software for us. I understand, we're developers, we're mostly lazy. And I have many opinions about large language models, but I will only share one thing with you. And that is that we must realize that we are forfeiting the opportunity to integrate our own cognitive perception within the software we are developing, and instead are replacing it with something which comes from a black box, which we do not know what it is. And I personally see that as a problem. We can take these three aspects of cognition and further define them, which I call our cognitive abilities. So on the mental aspect, we can think about cognition as separation between our rational system and our emotional system. And the beauty can be found in how they work together, where our rational system is the way we consciously think, but it's rather slow, albeit accurate. The emotional system is incredibly fast, and we are mostly unconscious about what's going on there, but it's sometimes completely irrational. The next aspect of cognition are our experience. And we can uniquely identify a human being by their experiences. So for all 8 billion people in this world by now, I believe for each and every one, their experience on this world is unique. And where the experiences are something of the past, they lead to expectations in the future, and that includes a certain bias in our approach to this world, and I think we should all be consciously aware about this. And whether this bias is positive or negative, we all have this bias, and because our experiences are so universal and diverse, there's no absolute truth to be found there. And then the last aspect are our senses. And while these include the 5 basic senses we all supposedly have, they also contain our interoceptive senses. So the feeling of being hungry and other needs we have. But the notion of cognitive abilities also implies the existence of cognitive disabilities. And I should mention, because cognition is such a complex construct, extraordinary abilities and crippling disabilities are not mutually exclusive, and so they can coexist within the same person. So on our mental aspect, we can say that we are dealing with mental illnesses, and in whatever shape or form. In our experiences, they can manifest as negative or traumatic experiences, which we need to deal with on each and every day. And perhaps our senses are the place where our disabilities are possibly able to manifest themselves in the most visible way. For example, being blind or being unable to hear things. And I think we should all be aware about that as well, where the cognitive disabilities are mostly invisible. But cognition in itself is not a fixed construct and can change over time. And So that brings us to what I call resilience. So if we see cognition as a problem-solving system, then resilience is the extent to which we are able to solve problems as they come up. And I would assert that a surplus of cognitive capacity improves our resilience, and as a consequence, we are better able to deal with problems as they arise. While on the opposite side, when overexertion of our resilience causes cognitive decline, deterioration. So that possibly leads to mental illnesses and poor mental health in general, where burnout is just one of the things which can happen to you. And to assess on what side you are on, I think it is useful to figure out whether you have a proactive response to events happening in your life, or whether you have a reactive response. Because if you have a proactive response, you can see these things coming and have the mental capacity to deal with them even before they become problematic. And so, in a sense, reactive or being reactive is incredibly tiring, but not because it is tiring in itself, but just because you do not have the capacity. And knowing this about cognition, it leads to the question whether we are using the notion of cognition as a recruitment tool or whether we are using cognition as an accessibility framework. And so, I want to drop this question with you. Are our discriminatory practices disguised as cognitive demands? So, are we seeing developers as resources which can be interchangeably applied, or are we looking out and caring for the individual? If you just need one reason to do so, I want to bring up Article 23 from the Universal Declaration of Human Rights, which states this: everyone has the right to work, to free choice of employment, to just and favorable conditions of work, and to protection against unemployment. But at the same time, rights cannot exist without responsibilities. Because rights without responsibilities leads to rights for some. And those who have these rights will have certain privileges. So that in practice, that means that the most vulnerable in society end up without rights. And I think that's something we should all collectively try to prevent. And for those who want to enrich themselves at the expense of others, I want to remind them of this quote from Alice Miller, who was a Polish psychologist and philosopher, who stated that people are free from depression when their feeling of self-worth is derived from the truth of their own feelings, and not from the possession of certain things or qualities. And this is a double-edged sword. It means that when you're dealing with depression, there's a way out. But on the other hand, that based on the current state of society, that many people are likely in a depressive state. And so, this leads me to the question, can the software industry be more accessible? And I think in order to explore this question, we should look at software complexity. And so I'm defining software complexity not by any notion of complexity, but instead by the cognitive abilities which are required to work with a given piece of software. And this includes the conceptual models of the software, so the objects from the real world we are expressing in our software. It includes the processes we are describing in our software. It includes the technical aspects. It includes the processes with which we develop software, and certainly includes the way that we use our software ourselves. I'm pretty confident that as soon as a blind person joins a software development team, that the software itself will be made more usable for this specific person, both in the process, both in the way the code is written, as well as in the way the software itself is being used. And so I personally celebrate diversity because it makes the world more accessible as well. At the same time, I'm creating a distinction in certain forms of complexity between natural complexity and irrational complexity. And natural complexity can be found in physics, for example, where complex natural phenomena can be explained by a relatively set of equations. But this isn't the case for irrational complexity, which requires context and which requires us to memorize things. And to a certain extent, this is inevitable, but I think we should all attempt to approach this natural complexity which we can more easily work with. And so, for the remainder of this presentation, I'm going to explore how we can deal with this cognitive complexity in software. And this has mostly been my own journey, and I'm disregarding a few best practices in here, but join me alongside. And so the way I develop software is like this. Some call it layered architecture, some call it the onion model. But the most important thing is that we have a domain in the core where we express our business rules, our business logic, in which we describe the real world around us. And everything else is certainly necessary to make it work, but not as important. Just curious, one of you are familiar with domain-driven design? Cool, that's a large amount. For those who are not familiar with it, I want to quickly explain it. So in my opinion, it basically contains about two important aspects. The first of which is the ubiquitous language, which attempts to create an ambiguous language about the things we are describing. And the most important thing about this is that we share this language with our peers. And perhaps more important than the language itself is that we properly describe the language. The additional important part from domain-driven design is the way we technically represent the real world. So we have value objects, which are basically immutable constructs, instances of which can be reduced across the domain. You can forget this one right away because it's not as important in this presentation. We have aggregates, which are basically entities and can contain entities, which contain a consistency boundary around them. So behavior in the aggregate cannot invoke behavior elsewhere, and any behavior in the aggregate must be triggered from outside of the aggregate as well. We have services which do not have this limitation, but they cannot maintain state as can the aggregate. We have bounded contexts which are related to the ubiquitous language as well, because the bounded context is not important as a technical concept, but more as a consistency boundary for the language we are using. And so in practice we find that the bounded context aligns pretty well with software teams working on certain aspects of the business. And then repositories are something related to data retrieval and not as important either. What is important, however, is that decisions made in the domain should be reflected everywhere in your solution. And so this has a certain impact on the software development process. So in this situation, we can move the greatest uncertainties up front, which reduces, therefore, the risk of innovation. And it reduces the risk of trial and error. And the goal here is to make the further implementation beyond the domain more of a formality rather than a process where risk may exist. And as I'm a glider pilot myself, I couldn't help but add an aviation-related graph in here. And, so this shows the... So some of you might be aware that most of aviation accidents happen during departure and arrival. And that's because the workload for pilots is highest in these phases. But at the same time, pilot capabilities decline as well during flight, so they become fatigued. which is why the risk during landing is highest. And so if we take this parallel to software development, we can base our process on the same principles. And so we start with a scoping process to determine what problems we want to solve. And then if we think we know what we want to solve, we can create a proof of concept in the domain. And if then at this point we figure out that what we came up with isn't really feasible, then we can just easily go back to the scoping process and try again. Not really a problem. And in practice, I find at times that these two parts of the process happen at the same time. So thereafter, we have the implementation of infrastructure, which really shouldn't take that much effort at all afterwards, at least in small companies. We continue with interface design, which is relatively high risk, but the risk would have been higher would we have started with the interface. And then we have some documentation and throw our whole package over the fence to be done with it. And so within the code I'm developing, I'm distinguishing between boring software and exciting software, and that's for a reason. Because there are many problems in software development which have been solved 1,000 times and will be solved 1,000 times more. And among these are data storage. I mean, so many of you are familiar with domain-driven design, that, which is also a problem which has been solved 1,000 times before. And I kind of want to get rid of that. And by creating a portion of software which we define as being boring, we also create space for software which is exciting, which is where we can unleash our creative abilities to solve actual problems. And on a high level, that would look somewhat like this. So we have a boring core in the middle. And around that, we get all kinds of, well, some might want to call it microservice architecture with interesting stuff. So experimental features, system integrations perhaps, interesting algorithms to automate business processes, and perhaps even AI systems and integrations. But why would we want to do so? And I think there are so many aspects to high quality software that we can't really do it any other way. So we have to deal with data organization, with concurrency, consistency. We don't want our data to be corrupted. We have to deal with scalability, and this is especially important in startups where there aren't all that many resources. And when the business model proves itself, a startup or the customer base of a startup can quite literally explode. And so we need to be kind of prepared for that without having to rewrite the whole code base, which we are in no position for then. We need to test code. We need to observe code in production. And because of that, we want the boring system to be incredibly stable as well. But most importantly, we want the development process to become a routine task. So it becomes some sort of muscle memory to navigate our way around the code base. And it becomes muscle memory as well to implement new behavior and to create experiments and kind of to follow the business in the daily realities instead of the business having to wait for the IT department to come up with whatever is required. And so this is kind of opposite for the exciting portions, which do not have to be scalable, which can just be experiments, which can be discarded at any time, as long as the main system keeps running. And so I want to take a moment to think about the way we are developing our domains on the technical level. We can use functions, which I will show you an example about in a moment, or we can use a message passing approach, which the remainder of the presentation will be about. And so an aggregate which is developed with this function-based approach in mind might look like something like this. There's quite a bit going on here. So first of all, we got state. We have a command, or at least I call it a command. We have our validation logic, and then we have the state change, all wrapped into one. And if only I would have started with software like this, I might as well not have burned out. So if this is the state of the code base you're working with, by all means continue with it, because it can scale pretty big. But it wasn't enough for me. Especially in an event-sourced environment, because the number of functions would kind of explode in that approach, where sometimes both the event handler and the command handler exist within the aggregate. But at the same time, I have seen the most crazy stuff happening within the aggregate as well, where external services were invoked and all kinds of nasty stuff you don't want there. And so, what I'm attempting to do is to make all these implicit behaviors more explicit, so that we can communicate about them, so that we know what is going on. And before I'm going to show you an example about that, I want to focus a bit on large-scale structure of such software. And this is where complexity comes into play again. So we can see complexity as the perception of multiple forces interacting with one another, creating complex phenomena, or at least they are considered to be complex as long as we do not know the forces which are interacting. And so I am all about layering complexity, because this allows us to approach problems from different perspectives. So within the software development teams, such approach allows the senior developers to focus on systemic change, while more junior developers can implement business behavior. So this in itself would make a code base significantly more accessible. And the large-scale structure I came up with over time looks a bit like this. So it resembles some bastard child between a domain-driven model and an event-sourced model. And so the different components, here I want to take some time to define them, because it's important. And there's only one component which can maintain state, which is the aggregate. And all other components contain behavior. Of course, it's a bit more nuanced than this, but that's the general gist. Starting at the smallest possible component is the event, which possibly mutates state. We have commands, which are responsible for the validation of our business behavior. We have services, which can be used to compose behavior and interact with external systems. And we have sagas, which are basically a temporal continuation of behavior. And so you might have noticed I have been using event sourcing as a first-class citizen, but that is not because event sourcing is so important. It's not about recreating state from events. It's a nice bonus that you can do that. That's not why I chose to do so. It's because event sourcing provides a clearly defined process for initiating change. So we create a command. We evaluate the command, we get the result, inspect the result to see whether we are allowed to make the change. Then we can apply the events resulting from there. And so this forces chunking up behavior, which is absolutely amazing for cognitive load. So we have very specific pieces of code we can focus on at a time. And when we see such a piece of code, we immediately know where it fits within the flow. And we can easily navigate our way around the code base as well. And so these abstractions force messaging, which allows us to generalize behavior handling these messages, which is nearly impossible when using function-based approaches in a domain. And then we would require reflection and whatnot, and it would become so enormously complex that I wouldn't want to deal with that. But these arrows hide something as well. And they are basically the relationships between the individual commands, but behind these relationships we can hide infrastructure, since infrastructure defines how the system interacts with one another. And so this way we can develop infrastructure only once and apply it for all business behavior we are developing. So in the daily practice, this means that we can solely focus on business behavior and not so much on infrastructure, which in small companies is absolutely a win, because we do not have to switch back and forth, and we can quickly iterate on the ideas we have, which was this slide. And so an additional aspect is the composition of behavior. And this is important because we do not want to write the same behavior over and over again. So when interacting with this system, there are two ways we can initiate change. We can issue a command, or we can issue a service, which sounds pretty weird, but will probably make sense in a little bit. And so a command is basically a small-scale structure, and a service is a large-scale structure. And so this is the way I want to compose code. If I have a service, I want it to call other services, which eventually call commands and initiate change. I can ramble on for a bit about how deterministic evaluation of code is important, but I'll keep that for another talk. So with this structure, we can eventually reduce any service invocation to a set of commands which describe the intent of the change we are doing. And this is incredibly important to be able to run this model in a distributed fashion as well as a local fashion. So again, within a small company, within a startup, even though we might not be at a point where distribution or scalability comes into place, we are kind of prepared for that, and it doesn't really matter how we run the software. But there is a small drawback to that, which is that it requires infrastructure to yield back the intent up the chain instead of down the chain, which is kind of the normal way we develop software. So we are inversing this direction. And so when we come at a point where we are able to evaluate a command, we only at that point we pull in the aggregates in order to validate the business constraints and, if possibly, generate the events describing the change. And then when we have an event, we can do a continuation to create another distinctive time step. And I want to mention that the temporal segregation of behavior is also an incredibly complex factor to trace down through time. So I'm mostly trying to prevent such things, although sometimes they are just necessary. Maybe interesting as well, there's a difference between the Saga and the process manager, which doesn't seem to be really understood. And so Saga generally is a stateless component, taking a single event and then triggering additional behavior, while a process manager is kind of like a Saga but with state. And because a process manager is fairly easily implemented using an aggregate, I'm just not interested in explicitly modeling that. And perhaps interesting at this point as well, a Saga is basically the same as a service but with a different way of invocation. So service can be invoked from the outside world, while a Saga only is invoked based on events. And so to remind you again, this is kind of the model we're working with. This is what I call code that fits in your head. Now we're going to discuss the actual code which makes such system run without the infrastructure that is. So generally we have, and we will find this sort of self-similarity all throughout this presentation. Generally we have an object describing the intended change and the handler actually providing behavior. And in case of an aggregate, the handler can generally be developed only once and reduced across the solution space, which isn't so much the case for the other domain components. But this is the general gist. And within the handler, we define the responsibilities of the aggregate. And this is what I mean by function-based messaging, because we have a method to evaluate the commands. We can apply the results. And something about snapshots, because generally do not want to expose the internal aggregate structure to the outside world because it makes it more difficult to change later on. And so we are abstracting that through snapshots. And this, in practice, is what an aggregate looks like. No behavior, just state. And so behavior is explicitly offloaded to commands and events. Again, to make implicit behavior more explicit. And so, to show you a few more code examples, this is what an event looks like. So we have a single object containing the stuff that is important to represent our change. And then we have a handler actually invoking the state change. In light of with further development of the system, we generally can only extend events but not delete them or change them. And so I prefer smaller events over bigger ones, especially because we can just discard events in place when no longer necessary. And at the same time, we have a high degree of freedom in the way we use the aggregate handler. You can just change that one, the event handler. We can just change that at any time. So we have a description of intent for which the object name is especially relevant as well. And we have the state change. This is the way that a command is structured, and we already start to see some of the self-similarity. So again, we have the object representing the command, basically a DTO, which is used for messaging in distributed systems as well. And then we have the handler, which contains a bit of evaluation. It describes the way that it should continue if successful. And then we just say, all right, this is fine, we can continue. And by explicitly returning error messages, we can be very specific about what is going wrong within our domain. And I think that is very important for traceability, for figuring out what goes wrong with the system. And so this is sort of self-similarity. And there is a similarity between the events and commands in the way that they can access the aggregate. There's similarity between the commands and services in the way that they can evaluate behavior. And then there is similarity between services and sagas as well in the way that they can basically do anything, but there is more or less a difference in the way that they are invoked. But on all these objects, we see the distinction between the object requesting the change and providing the information and the actual handling of the object. And so this self-similarity is one of my favorite tools to reduce the cognitive complexity of software. Just change it slightly enough that it is still recognizable as a distinct piece of behavior, but keep it similar enough that it can easily be recognized as to what it is doing. And more importantly, can easily be memorized. And so, in practice, this is what domain interaction looks like for me, based on the code I just showed you. And personally, I'm a sucker as well for folder structures, because it allows me to navigate through the code base. And the cleaner it is, the better. And so I'm mostly organizing software based on the business role they fulfill. And then within that is distinction on the role. So a few notes. Coupling is mostly one-to-many, which is relevant for commands and events, for services and commands. And most things can change independently. I want to take a small bit of time to focus on infrastructure, and mostly I'm not interested in infrastructure anyway, since it's a big messy place. I want to be involved with at least amount reasonably possible. But I think it is interesting because this is the place where we can implement an actor system. And so for those not familiar with an actor, it can basically be conceived as being a unit containing isolated storage, as being able to compute things, and as having an ability to communicate with other actors. And this is a brilliant abstraction over hardware concerns, and so I'm using it to run this domain in a distributed fashion. And although it is still infrastructure, I'm creating its own distinctive space for it as well, because that allows me to tune the distributed system independently from the behavior running on it. And so, in this model, a single aggregate generally translates to a single actor. And all the components can be run in whatever fashion you deem fit. And so, in our case, the actor system is only just a proxy to domain behavior. Nothing more, nothing less. And this is what provides the scalability properties pretty much free of charge. And so this is a somewhat simplified example of what it looks like on Orleans. So we have the same behavioral contract implementation again as mentioned previously, which is the aggregate handler. But now we are providing a different implementation, and we are only truly routing behavior through the actor straight into the domain. It is pretty amazing because it helps us to preserve domain concepts across multiple layers. And so the unit tests I'm writing to test domain behavior are exactly the same way I would interact with this actor system, which is amazing. So we have some sort of self-documenting system where we can just copy bits and pieces from the tests over to the software we are writing to interact with the domain. And so the APIs themselves merely become tin mappers as well, mapping the HTTP arguments over to, or routing it into the actor system, and which eventually routes it further into the domain itself. So APIs become rather simple as well, and this makes it more easy to implement multiple APIs as well. So we can create a GraphQL API if we were interested in that, and we can create a REST API, and they're just tin mappers anyway. We only need to care out for future maintainability and people relying on these systems. So at this point, we are out of the onion or the layered architecture or whatever, and we can move into the front end. And I can assure you, as I have done front-end development as well, that such approach makes front-end development so much easier because we are able to directly interact with the domain. And so, since the same concepts are preserved, we can reduce them on all layers in our solution. And so, this is basically what I consider to be the benefits of transparency. And consequently, few moving parts result in less bugs and less time spent fixing bugs and less time spent firefighting, which I absolutely abhor. And so this brings us back to the original question. How does complexity relate to cognition? And I think that complex software is an occupational health hazard. Or maybe not. Maybe it is cognitive depletion, which is an occupational health hazard. There is one OSHA category called work organization hazards. And it is defined as follows. It contains the following things: workplace violence, discrimination, lack of respect, sexual harassment, and other conditions hazardous to mental, emotional, and physical health. And within software development, we are susceptible to that as well. And so basically, as soon as the business, its risk of complexity is offloaded to employees, we are all in risk. And I wouldn't let that happen to myself. I want to prevent myself from having to carry this burden. So, what can we do? We can reduce the code complexity, which frees up our cognitive abilities. We can reduce the cognitive demands, which consequently improve our resilience. And I think the reasons to do so are pretty much self-explanatory. It reduces the development cost because we are able to move faster at improved product quality. And perhaps most importantly, it improves developer well-being. And so our mental well-being, or well-being in general, is basically the first requirement we need to satisfy, because before we are able to solve problems. And problems we must solve, for example, the climate crisis. And I think this is one of the biggest problems we have to deal with. And there are people warning us, Greta Thunberg among us. She proclaims, our house is on fire. I'm here to say, our house is on fire. And this is how we respond. I think this is pretty much recognizable in the world of software development, where we are continuously firefighting, and I want to move away from that. And so we are on track to 3 degrees of warming on Earth. And this is how we should respond. And this is perhaps how we should respond in software development as well, in the software industry. So systemic change is required. And how are we going to achieve that? How can we live more sustainably if our self-worth is defined by our possessions and not so much on the truth of our own feelings? And so Carl Sagan, the late American physicist, was a bit more skeptical about this. He stated, "Extinction is the rule, survival the exception." Thank you very much.